Section 3.2 talks about logarithm functions and their graphs. So what we'll look at is evaluating logarithmic functions that have a base of a and what that graph looks like. And then look at the natural logarithmic functions and then what those functions look like as well. So first, in just the general logarithmic functions with base a, couple things here. X has to be greater than 0. So we'll get to this in a little bit, but the domain of your logarithmic functions are always 0 to infinity. You can't take the log of a negative number. So you can't take the log of a negative number or 0. And then your base of your log will also be greater than 0. So that will always be positive as well. So when we have this equation, y equals the log base a of x, that's true if we could put it into exponential form. So if we took the base, which is a, and we raised it to the power that it equals, which is y, if that equals this x value, then those two things are true. So when we have the function notation, we would say that f of x equals the log base a of x. So every logarithmic equation can be written as an exponential equation, and every exponential equation can be written as logarithmic. So what will happen is we'll have to be switching between the two depending on the problem to potentially help us solve. So again, if we have y equals the log base a of x, we could also write it as the base raised to this power equals this value. So let's work on doing that in this next example. So if we have to evaluate when x is 32, so if we said that y equals the log base 2 of 32, substituting 32 in for x, if we were to put this into exponential form, we would say the base, which is 2, raised to the y equals 32. And so then you'd have to think, well, what to the y, what 2 to what power is 32? And we would get that y would equal 5. So when we look at b, if we have x is 1, we would say y equals the log base 3 of 1. So if we were to put it into exponential form, we would take the base to the y and set it equal to 1. And 3 to what power is 1? We would get 0. So the log can equal 0. You just can't take the log of 0. When we look at c and we substitute in, we would have y equals the log base 4 of 2. So if we were to put that into exponential form, 4 to the y equals 2, and we would get that y is 1/2, right? Because the square root of 4 is 2, so y would have to be 1/2. And then for d, when we have y equals the log base 10 of 1/100th. So if we put it into exponential form, 10 to the y equals 1/100th. One little trick here is that when you have a fraction, it might make sense to rewrite this. So instead of saying 1/100th, we could say 100 to the negative 1. And then try to get your bases to be the same. So 10 to the y, we could rewrite that as 10 squared to the negative 1, which is really 10 to the negative 2. And now that those bases are the same, now we could tell that y equals negative 2. So the logarithmic function with base 10 is called the common log. So if you don't see a base, if you just saw a problem that said like y equals the log of 2, if the base isn't written, it's automatically assumed to be 10. And that's what your log button on your calculator, the one right next to your number 7 button on your calculator, that uses your base 10. So some properties are anytime that you take the log of 1, you'll always get 0 because if you were to put it into exponential form, that a to the 0 is 1. And we did one like that up above here in letter B, right? When we said we were taking the log of 1 and we ended up with 0. Whenever the base and this base are the same, it will always equal 1, or it will equal whatever's in the exponent. So another one would be like if you had the log base a of a squared, it would actually equal 2. So when those bases are the same, whatever you have up in the exponent is what your answer will be. That's actually number 3, getting to that one. The log base a of a to the x, you'll always get x. And if you have the log base a of x and it equals the log base a of y, then whatever you're taking the log of would have to be equal to each other in order for those two sides to be equal. So let's use the properties. For a, if we're solving, so this is if we have the log base 2 of x and it needs to equal the log base 2 of 3, in order for these to be equal, then these two parts would have to be the same. So we would know then that x has to equal 3. In B, we want to solve for x. So what does this equal? Remember, when we have the base and the base, whatever's in the exponent is what your log will equal. So in this case, x would equal 1. If we look at C, we have those same bases again. So whatever's in that exponent would be what it would. In this case, it's what it simplifies to, because if you notice, there's no equal sign on this problem. So you're not actually solving for a value, you're just simplifying it. Same thing with D, we're simplifying. Now we haven't seen one like this, but again, if you look at it in reverse, you have a base 7 and a base 7. So whatever you're taking the log of is what it ends up simplifying to. So that one would just simplify down to 14. So the graphs of logs are actually the inverses of exponential functions. So they're just the switching of the x and y. So if you look at this example, if we graphed 2 to the x, I'll go highlighter on this one. If we graph 2 to the x, you get this graph right here. And if we graphed the log base 2 of x, you get its inverse. So your x and your y values are switched. Notice that with your log function, your domain, remember, is still 0 to infinity. Right? When your exponential function crossed at the point 0, 1, your log function will cross at the point 1, 0. Instead of the x-axis being the horizontal asymptote, it switches, and now the y-axis is the vertical asymptote. So this is just that kind of that slide that gives you that information. Your domain is all positive real numbers. Your range is all real numbers. Your intercept is at 1, 0. It's increasing over the domain. And your y-axis is your vertical asymptote for it. So this is kind of that basic graph of any log base a of x function. Right? We have this vertical asymptote at the y-axis. It crosses at the point 1, 0, and then it just increases over the domain. So then we get into the natural log. And remember, our natural exponential function had the base e. So your natural log has a base e. So if we have y equals the log base e of x, instead of having to write it as the log base e, that's just the same thing now as the natural log of x. And so if you look at your calculator, right under your log button is the natural log button. So whenever you see the natural log of x, it really means a log base e. So that base of that natural log is your e value. So if we were to use our calculator just to kind of get the hang of using natural log, so everyone find your natural log button. So for a, if we're taking the natural log of 2, and again, we're going to go 3 decimals, we should get 0.69 0.3. If we have the natural log of 0.3 for b, we get negative 1.204. If we were to try to take the natural log of negative 1, if you type it into your calculator, you get an error, non-real answers. Because remember, you can't take the natural log of a negative. So there's no solution when you try to take the natural log or the log of a negative value or of 0. And then the next one, the natural log of 1 plus root 2. And you can take natural logs of irrational numbers. They don't have to all be whole numbers. So when you type that in for D, you should get 0.881. So some of the rules for natural log are the same as the rules for log. The natural log of 1 is 0, again, because you're just really taking the log of 1. In this case, the natural log of e is 1, since remember, it's just kind of that unwritten rule that the base is e. So the natural log of e to the x is whatever's in the exponent. And if you have the natural log of x equaling the natural log of y, then x would have to equal y. So if we use some properties to rewrite, so instead of saying the natural log of 1 over e, we could say the natural log of e to the negative 1. And then to simplify that, remember when we have that base e and the other e, this would actually simplify to just be negative 1, whatever's up in that exponent. For b, when we have the e base and this e base here, remember it just simplifies to be whatever we're taking that log or the natural log of. The natural log of 1 is 0, so we're really doing 4 times 0, which would be 0. And the natural log of e is 1, so you would have 2 times 1, which would give you 2. So in the next example, when we're looking at domains of log functions, so we really have to think about these as transformations. Remember that the domain of your log graph and your natural log graph is 0 to infinity, and then we're talking about x values. So we have to think about how it's shifting. So here, this x minus 2 tells us that we have a shift to the right 2. So if our domain shifted to the right 2, then it would shift over to be 2 to infinity. All right, so if you look at the picture here, that normally we have that vertical asymptote at 0. That vertical asymptote would shift over to 2, which means our whole domain shifts over to 2. Now when we look at b, this one's a little bit trickier. For b, we might want to rewrite that as the natural log of negative x plus 2. And so in that case, we actually have to have that negative by itself. So we're going to factor out the negative, and then we have x minus 2. So once we write it like this, and we talk about the transformation, we know that we're going to reflect our x values. So we're going to have a reflection over the y-axis, and then we're going to shift, struggling with my writing, shift to the right 2. And so when we look at that graphically, when you reflect over and you shift to the right 2, you end up with this graph. So your domain would be negative infinity to 2. And then for C, when we look at the graph for C, the natural log of x squared, this would be one that you graph on your calculator. And so when you graph this, if you notice, it actually graphs right here, right? So you end up with that your domain for this one would be negative infinity to 0, and then 0 to infinity. So it would really be all reals not equal to 0.